Hello friends, a very good morning. Hope everyone is doing safe, healthy. In this video, we will be discussing about conductometric titrations. So what exactly titration that means? Already we discussed. Just a recapitulation. The process of adding a reagent from the burette to the other in the conical flask to find out the concentration of a given test solution. So what do we mean by metry? Measurement. Conducto, that stands as conductance. So titrations in which we measure the conductance. Is that the thing we have to determine? But the answer is no. What we have to determine? We have to determine the concentration. How do you determine concentration by conductance? Let's see. So in my previous videos, you can go through electrochemistry video 1. You find different types of conductances like molar, specific and equivalent. In case of conductometric titrations, we will be finding out the specific conductance. So everyone knows that specific conductance is defined as the conductance offered by all the ions present in a fixed volume, in a specified volume. Say for example your classroom that I told in that video, it will come as an iCard. You can just go through it once again. So your classroom, the volume is fixed. How many ions are there? Say for example 30 ions are there, and all these ions will move, will make some noise. That's what we exactly call as specific conductance. What are the units of specific conductance? Moles per centimeter or Siemens per centimeter. What are the factors that influence specific conductance? Here are temperature, number of ions, size and charge of the ion, concentration, otherwise dilution. I discuss all these concepts again in that video, electrochemistry part 1. Please go through, please visit. So what is the effect of temperature on conductance? So I prepared 4 solutions of different concentrations where I changed the temperature from 20 degrees Celsius to 60 degrees Celsius. In each of the solution having variable concentrations, as the concentration is being changed, regardless of the change in concentration, when the temperature is being increased, specific conductance of the electrolyte solution is also getting increased. This point has to be understood because the average kinetic energy increases. Then number of ions, more the number of ions, more will be the conductance. So this is very easy. If in your classroom one student is there on that day, on a particular day only one student is there in the classroom, he can't do any nonsense, he can't do any noise. He will just go into his place, sit quiet, calm and do his work. If he want to leave the class, he'll go out. That's it. 2 students, they can have some chit chat. 3, some noise. 30, wonderful noise. So more the number of ions, more will be the conductance. Then what is the relation between size and conductance? It is from we derive it from the expression called kinetic energy expression. So Ke equal to half mv square. From this equation, if we rearrange it, how would we arrive? So V equal to square root 2 Ke by m. So what is V? V is nothing but velocity. Velocity is nothing but the mobility of ions. Mobility, that is movement, and that in turn related to conductance. So velocity is inversely proportional to m, mass of the ion. So least the mass, highest will be the mobility. Highest the mass, least will be the mobility. Okay. Then we are measuring specific conductance in case of conductometric titrations. Hence specific conductance decreases on dilution. Specific conductance decreases on dilution. See, to make you understand, just a simple paint diagram I made it. Try to understand. So in the left hand side diagram, I have taken a big basket in which I wish to measure the number of ions present in a small volume. The small volume is shown, the small rectangular portion. the big square portion is the entire volume. So how many ions are there in this small square portion? 2 plus 3, 5 ions are there at the start. But when we add water on dilution, what had happened? The number of ions present in the small square portion got decreased. That means 3 ions will jump away from the small square. To make you understand, your college or school, mostly college, is the big square box. Your classroom is the small square box. So your classroom, 30 students are there. Suddenly you got bored of the lecture. You bunk the class. Where will you go? You will be there in the college only. Remember it. You will be there in the college only. You don't have the permission to leave the main entrance of the college. But you are not there in the lecture hall. So the number of ions in the lecture hall will be decreased, and hence on dilution, specific conductance decreases. Then during conductometric titrations, we have to take care about volume correction, because as mentioned earlier, on dilution, specific conductance decreases. Say for example, you are doing an acid base titration by conductometer, by using a conductometer. So whenever you titrate an acid by using a base, for example you are titrating HCl using sodium hydroxide, whenever you add sodium hydroxide solution drop by drop into the solution of HCl, the H plus ions present in the HCl solution will be replaced by the OH minus ions present in the base, and they form salt and water. H plus ions will be replaced by sodium ions, and there will be a reaction between. So HCl plus NaOH, that gives you NaCl plus water. So what had happened? Number of H plus ions will decrease automatically due to neutralization of H plus ions. Due to neutralization of H plus ions, there will be a decrease in the conductance. But you are adding sodium hydroxide solution. Whenever you use the word solution, it is a combination of two components. One is solute and the other is solvent. So your sodium hydroxide solution has water in it. Whenever we add water, it is what generally we call as dilution. Whenever dilution is done, specific conductance decreases. So during conductometric titrations, the decrease is observed due to two factors. One is due to the chemical reaction between the acid and base, and due to the dilution effect. To correct this dilution effect, we have to go for volume correction. So to make it happen, another example I have taken. Say for example, I have added 0 ml of sodium hydroxide, which means I did not add any sodium hydroxide, and I observe a conductance value as 10.9. Then I have added from the burette into the beaker 0.5 ml of sodium hydroxide solution. Then I found 8.6. There is a decrease. Naturally, we think that it should decrease because H plus ions will react with OH minus ions and they form water. So there will be a decrease in H plus ions. So whenever the number of H plus ions decreases, conductance decreases. But we are adding sodium hydroxide solution. That solution contains water, and as water is being formed in the reaction, it causes dilution effect. So this decrease may be due to two factors. One is added sodium hydroxide solution, the other is dilution. So just subtract the values. 10.9 minus 8.6, I got 2.3. This 2.3 is due to the two factors, 1 and 2. Now what I have to do? I have to do volume correction. How do I do it? So C dash, corrected conductance C dash, is equal to C into V plus 50 by 50. Sir, why you have taken 50? Because the total volume of acid is 50. I have transferred 25 ml of acid and 25 ml of water. Total volume is 50. Should I take only 50? No. You can take 75, you can take 100, you take whatever the volume, that volume should be added here. What is the value of C here? 8.6. 8.6 into 0.5 plus 50 by 50. So how much is the original value? Is 8.686. So what is the value that you have to obtain? It is 8.686, but what you got, it is 8.6. Why the small difference? The small difference of 0.08 is due to the added solution from the burette into the beaker. This is what we call as dilution effect. Then this is a simple flow chart, like as we are going to do the experiment with strong acid, strong base. Strong acid, hydrochloric acid I have taken, and strong base I have taken sodium hydroxide. Here in this experiment, both strong acid and strong base are secondary standard solutions. That means their concentration changes from time to time. To standardize sodium hydroxide solution, we are in need of a primary acid, and that primary acid solution is oxalic acid, but mostly potassium hydrogen phthalate is preferred. It is used, but for convenience for undergraduate students, we prefer to use oxalic acid solution. So first you prepare oxalic acid solution as shown in the flow chart by weighing bottle, then transfer into 250 ml or 100 ml volumetric flask using a funnel, dissolve the substance in distilled water, then make the solution up to the mark. Then second process, our second step, standardization of sodium hydroxide solution. Pipette out 10 ml of the oxalic acid solution, add 20 ml of distilled water and use phenolphthalein. Only one drop is sufficient. So when you titrate by adding NaOH from the burette into the conical flask, the end point is observed by the color change from colorless to pale pink. Colorless to pale pink. Colorless in acid medium. Phenolphthalein is colorless in acid medium, whereas phenolphthalein is pink colored in alkaline solution. Using the formula M1V1 by N1 is equal to M2V2 by N2, you will be calculating the concentration of sodium hydroxide solution. Now step 3, you will be given a test sample solution. Say for example, you were given a sample of HCl from some industry or from some other sources. Then immediately you have to make the solution up to the mark using distilled water. Then from such a solution, after thorough mixing to make it homogeneous, what do? We transfer 25 ml of HCl solution into a beaker. Then we add 25 ml of distilled water to the same beaker. We insert the conductivity cell and we will calibrate the instrument as prescribed by the manufacturer. Then we will add gradually 0.5 ml of addition. So your tabular form will be serial number, volume of base added, conductance, C dash, corrected conductance. Say first value is 0. You have to note down the conductance of acid solution as it is. Then add 0.5 ml. What is the total volume? 0.5. Record the value. Add another 0.5. What is the total volume? 1 ml. Record the value. Go on gradually adding 0.5 ml, but the total volume should be noted down carefully. Then you will be getting C values. Calculate C dash by using the formula C dash equal to C into V plus volume by volume, and make ready with volume of base and corrected conductance values. Now you have to plot a graph by taking volume of NaOH on x-axis, that's abscissa, and on ordinate you have to get with the corrected conductance values. Then as a strong acid, it will exhibit high conductance. So if you observe, the point A in the graph is highest conductance value. It is getting decreased. It is getting decreased because the number of H plus ions will be getting decreased. Then it reaches a point where all the H plus ions taken in the beaker becomes completely neutralized. From then the C point, C to D graph, A to B, C to D. C to D are the OH minus ions, represents the OH minus ions. How to plot a graph? First you have to plot all the dots, all the points on the graph sheet. Then draw two straight lines in such a way that the two straight lines must intersect. If they don't intersect, you have to extra plot the graph. If you may miss some points, doesn't matter. You have to draw two straight lines using a ruler, and then the point of intersection will be taken as the equivalence point or end point. So this is a graph for weak acid and strong base. Weak acid, as the name suggests, its dissociation is very less, so you cannot find the ions as strong, so it will show a very less conductance. And whenever you add a base, there will be a salt getting formed, and that salt that is formed will show a gradual increase in the conductance. When after all the ions got completely formed as a salt, you will get your neutralization point. From then the graph shown as a tick mark. Then these two are the graphs. Left hand side, strong acid versus weak base. Weak base is ammonium hydroxide, and strong acid, that is HCl. And on the right hand side, it is for weak acid versus weak base. So I have taken acetic acid and weak base as ammonium hydroxide. These are the different graphs which we obtained. So what is the advantage of instrumental version over classical methods? In classical methods of analysis, where which we use indicators, there we will be measuring the end point. But in case of instrumental methods, we will be finding out the equivalence point. Exactly, we will be calculating the concentration of given solution. So please leave comments, please do subscribe, like and share. Thank you.